Alright, today we're going to be discussing the Earth's moon. It is the only satellite that we have around the Earth that's natural. It is the first moon in the solar system. Mercury and Venus do not have moons. And it is also one of the largest moons compared to its planet size. Now, the moon is 1/4 the size of the Earth, diameter-wise, which allows them for only 1/6 the gravity on Earth. So if you were on the moon, you would weigh 1/6 what you weigh here. So you weigh 120 pounds on Earth, you weigh only 20 pounds on the moon. Now, the moon has no atmosphere. It has a very trace amount of gases. And because of this, it is heavily cratered. One reason why, because there's no weather. So if an asteroid or something hits the moon, it creates a crater. That crater does not get covered up or worn away over time by weathering. And also, there's no atmosphere to burn up the smaller pieces before hitting it. The Earth has an atmosphere, and smaller pieces of rock that enter it burn up, and so they never hit the ground. But on the moon, anything that comes near it will probably hit it. Now, the temperature on the lit side is 100 degrees Celsius, and the temperature on the dark side is negative 170 degrees Celsius. Now, the line that separates light and dark on the moon is constantly moving, and it takes about a month to cover all the way around the moon. So, whenever we planned a trip to the moon back in the late 60s and 70s, we always wanted to make sure that we were there kind of not when it's 100 degrees out, but definitely not when it's dark, so kind of in between, so a little bit more tolerable. Now, there's no liquid water on the moon that we can find, mostly due to no atmosphere, but there's ice suspected at the poles, and there are a couple of missions in the last couple of years where we had satellites crashing into the moon to try to kick up ice. It's estimated that there may be large amounts of ice at the two poles or in some very deep craters on the moon. Now, one reason why we like the moon so much for future space travel is the escape velocity of the moon is 1/5 that of Earth. Escape velocity is how fast you need to be traveling to leave the gravitational pull of the planet. Now, the moon's orbit around the Earth is elliptical. That means it's not circular. It's an ellipse, which is kind of like a flattened circle. The average distance from center to center is 384,400 kilometers, but that can change. At apogee, it's when it's farthest away, and perigee is when it's closest. And the upcoming full moon is actually going to be the largest full moon for us because it's going to be the closest it's going to be at full moon for a while. Now, the plane of the moon's orbit does not lie in the same plane of the Earth's orbit around the sun, which means that we kind of have two circles happening on our orbit. So let's say here's a line here, and we have the Earth, and we have the sun, and we are orbiting around the sun on this line. Well, there's another line kind of going like this that the moon lies on, and it goes at a different angle than our path around the sun. And so they hardly ever line up. They only do a couple times a year, and that's typically when we have eclipses. Now, one of the really cool things about the moon is that it has what we call a synchronous rotation, which means that as the moon revolves around the Earth, it also rotates on an axis that a period that is the same as the orbital period. That means it takes the same amount of time for it to go around the Earth once as it does to rotate once. So this causes it so that we only see one side of the moon ever. We've only seen one side of the moon ever in the history of the moon. And so we always have one side facing us. We never see the other side unless we've been there, orbiting around in the spaceship or with satellites taking pictures. And so the other side of the moon is always referred to as the far side of the moon. So we have here two pictures. We have the near side on the left and the far side of the moon on the right. Now, on the near side, you can see these darkened regions. Now, they are caused by magma escaping from the moon. And so we can tell that there used to be some sort of volcanic activity, or this could have been caused by almost tidal forces early in the history of the moon, but they're very darkened regions. You can see some cratering taking places. You can see some of the streaks that happen around the craters. When Galileo looked at the moon in the early 1600s, he called these darkened regions seas, or the term we use for that is Maria. And so we still call them Maria. But you can still see a tremendous number of craters on the moon. If you look closely at night, you can almost see some of the larger ones. Now, the far side of the moon, which is on the right here, has a tremendous number of craters because that's the side always facing away from the Earth. So if you have an object coming towards the Earth, it's more likely to hit the far side of the moon than the near side of the moon. The near side of the moon almost has us kind of protecting it. And even though there's a great distance between us, we do kind of protect the moon a little bit from one side getting hit. Now, the moon formed, and the leading theory to this is the formation of the moon is giant impact theory. When we look at moons of other planets, we try to figure out how did that moon get there. With Mars, it's pretty easy to figure out that those two small moons it has were probably just captured asteroids from the asteroid belt. We look at some of the moons of, Jupiter or Saturn or Uranus or Neptune, and we try to figure out, how did they form? The orbit around the planet, the size of the moon, all this helps us try to understand how did it form. Now, our moon is really, really big compared to the size of the planet. Compared to other planets, anyways. I mean, it's still only 1/4 the size, but it's big. I mean, that's kind of big for a satellite. And its orbit around us. Now, its orbit actually changes over time. The moon is constantly getting a little farther away from us each year, and we can measure this because during one of the moon landings, we actually place a huge set of mirrors on the moon, and we're constantly shooting a laser at that and bounces back, and the moon's actually getting farther away. So taking it all into account, and using computer modeling, we actually came up with the giant impact theory, which says that the moon formed from debris expelled when the Earth was struck by a glancing blow by an object perhaps several times as massive as Mars. So you have to think kind of the early solar system. We had the Earth here. Mars is the next planet out now, but in between would have been another object. And its path brought it too close to the Earth one time, and it just collided. The debris would have been mixed up with some of it coming into the Earth, some being ejected from the Earth, and what would be ejected would have formed a ring pattern around the Earth, which would have coalesced into the moon. This is kind of a step-by-step path how this would happen. So a Mars-sized body hits the primitive Earth. We see some ejection of material from the Earth and some collection of material from the Mars-sized body. And then we get this cloud forming around the Earth, which would form into the moon. There's a certain kind of distance away from the Earth that this would be needed. And we look at that with other planets where, Saturn has a ring system right now, but the objects in that ring system are too close to the planet. They're slowly getting pulled in. And so eventually Saturn's not going to have any rings. So our object was just ejected far enough out that formed into the moon. This is another little animation kind of showing this. The object hitting the Earth, and then you see the collection material. Pretty basic how it will form. We actually used computers that were designed to test explosions from missiles to come up with this. It was analyzing the data from the impact. And even though it seems kind of, a once-in-a-lifetime shot, kind of think about a really difficult pool shot, all the evidence is pointing towards the moon forming this way. Now, the lunar landscape is very interesting to us. We've had astronauts walking around on it. There are mountains, there are valleys, there's craters, and there are suspected deep caves in there. Before the telescope, not information was gained about the surface. Galileo used it to make observations about different types of terrain on the moon. And like I said before, dark parts he called seas, which we call Maria. The lighter parts he called land, which we call terre. Now, there are no seas on the moon. It's all land. Again, no liquid water. So that's pretty much what the moon is.